guys, welcome back. Today we are going to be covering Chapter 5 on function creation and selected MATLAB functions. There's a lot to cover in this chapter. I'm going to try to go over it as quickly as possible. I really want to focus this chapter on showing you how to do it in MATLAB. But before I do that, as usual, I'm going to go over the PowerPoints just to kind of give you the general idea of what the content and topics discussed are from the text in regards to function creation. So we have several different sections we need to go through. We're going to do user-defined functions, function handles, functions that can operate on arrays of data, functions that require user-defined functions, and then symbolic solutions and converting symbolic expressions into functions. So as you can see, there's a lot to go through here. So objectives. Describe how functions are created and give numerous examples of MATLAB functions that are frequently used to obtain numerical solutions to engineering problems. Why do we use functions? We use it to avoid duplicate code, limit the effect of changes to specific sections of a program, promote program reusage. We can also reduce the overall complexity of the program, improve portability. It also makes debugging easier in certain cases. So there's lots of reasons why we might want to use functions within MATLAB. So we're going to start with the basics here. Function files are script files that create their own local and independent workspace within MATLAB. Variables are defined within a function. Variables that are defined within a function are local to that function. So that means that they cannot be affected by any other variables outside of that function. Also, MATLAB's functions, all of them are of this type. So again, when you create a function in MATLAB, any other variables, let's say in your function you have x is equal to something. If you're in your command window or you're using some other function or script, if you assign x to be equal to something else, it's going to be totally independent of that because it has its own local workspace for the variables. And the only exception is the global function, which creates global variables which can be accessed outside of the function. The first non-comment of a line in a function must follow a very prescribed format from MATLAB. So in general, the names of functions should be chosen so that they are meaningful and indicate what the function does. So let's say that you have a function that is plotting some sort of polynomial. You might want to call that function plotting polynomial, just because it's easy to identify that. Now, in this particular class, I am going to have you guys use a specific naming convention for your function files. In the past, we haven't done this, and it really creates a lot of confusion for students. A lot of times their functions wouldn't actually run just because of simple naming convention type things that I guess weren't really clear before. So again, in the next video, be sure you watch that because I'm going to specify for you guys how you should go about naming your functions. I'm going to do all kinds of examples for you. The typical length of function names are anywhere between 9 and 20 characters, and it should employ standard or consistent conventions. Again, I'll go over those. The proper choice of function names can also minimize the use of comments within the function itself. So in other words, if you name the function something that's relevant to what it does, then you're not going to have to use a bunch of comments within your code or your program to explain what it is that the function is doing. So you have 4 ways of creating functions. We can create a function file, and that's created by the command function. And when it's saved in a file, so it'll be subsequently accessed by scripts and functions or from the command window. We also have subfunctions, and when the function keyword is used more than once in a function file, then all of the additional functions below that first one are considered a subfunction. The subfunctions are only accessible by the main function of that file and all other subfunctions within that main function file. They are used to reduce the number of function files that you have to create. So ordinarily with a function, you might have to, in the past you used to have to create a separate file for every single function that you created. Now you can do subfunctions within one function so that they can all be placed into one file. We also can create anonymous functions, and this is a mean of creating functions for simple expressions without having to create M files or sub-functions. It is accessible only from the script or function in which it was created, and an anonymous function can appear in another anonymous function, and an anonymous function doesn't have to be saved in separate files. We also have the option of using the inline function, and when functions are created with the inline command, they are limited to one MATLAB expression. It is accessible, again, only from the script or function in which it was created, and the MATLAB expression cannot refer to other inline functions or sub-functions. A function that is going to reside in a function file has at least 2 lines of program code. The first line has, again, a very specified format required by MATLAB. And the name of the M file should be the same as the name of the function, except the function has the extension .m, which we've seen in previous videos. Again, I'll go over that in the next video where I show you how to do all of this in the MATLAB IDE. So with function files, the number of variables and their type, meaning scalar, vector, matrix, string, or cell, are brought in and out of the function and are controlled by the function interface, which is the first non-comment line of the function program. In general, a function file will consist of the interface line, some comments, and one or more expressions. So let's take a look here. This is an example of a function file. So you can see we chose to use that function command, and then we have these square brackets. Inside the square brackets is where you put your output variables, and then equal to your function name. So you can name this, again, something that's relevant to what the function is doing, and then input variables. So these are the variables that are going to be input into these expressions down here. And then once these are evaluated, these output variables will be displayed to the command window. So that's essentially how they work. So output variables, again, is just a comma-separated list of names of the output variables, and then input variables is a comma-separated list of the names of the input variables. The function file may be stored in any directory and has the file name function file. Again, just good practice, save it within that MATLAB folder that I showed you guys from chapter 1, just because then they're easily accessible. You can locate them anytime you need to execute them at some point in the future. So this shows more of the syntax where you would actually have variables inside. So V1, V2, V3 are your input variables. A and B, so on, would be your output variables. So we do have some special cases when creating functions. Functions can be used to create a figure to display annotated data to the command window or to write data to files. In these cases, no values are transferred back to the calling program. So as you can see here, it's just function name, input variables. So you can see there's no output here. We're just inputting variables into a function. We also have a second special case. When a function is used only to store data in a prescribed manner, the function does not require any input arguments. In this case, the function interface line has this form. So now you can see we have function output variables, our function name, but there are no input variables here to the function. When a function converts a script to a main function so that one can decrease the number of function files, you have to use this syntax here. Make note of this. This is going to be really important, especially when we get into solving ordinary differential equations in MATLAB. You will need to use this. So basically at the very top of your file, you're going to use function name. This function name here should match the name of your .m file. So again, use those naming conditions. So it would be, something effective function lin underscore neskin underscore homework2 or whatever. And then after that, you can put as many other functions and sub-functions as is necessary for your program. So there are several concepts that must be understood to correctly create functions. The variable names used in the function definition do not have to match the corresponding names when the function is called from the command window, a script, or another function. It is the locations of the input variables within the argument list inside the parentheses that govern the transfer of information. So what does that mean? Let me go back here and show you. So when we're looking at this here, when you're passing these variables in, it is the order of these that are relevant, not what the specific variable is. So the names selected for each argument are local to the function program and have meaning only within the context of the program. We talked about that. The same names that can be used in an entirely different context than the script files that call the functions or another function used by this function. So they can be used in an entirely different context, is all that's saying. However, the names appearing for each input variable of the function statement must be the same type. So a scalar, a vector, a matrix goes with a matrix, and so on. So just be sure you're aware of that. If the input argument is expecting a vector, you can't enter a matrix there. You're going to have to enter a vector. The variable names are not local to the function, we talked about this too, only when they have been assigned as global variables using this global syntax here. So again, that was one of those key words that was reserved exclusively for MATLAB. So consider the following two equations that are computed in the function. We have x equals cos of AT plus b, and y equals the absolute value of x plus c. The values of x and y are to be returned by the function. The function will be named computeXY and saved in a file name computexy.m. So let's take a look. Here's our example. So we've created a function. Again, our output variables are x and y. Here's the name of our function, which must match the name of our file that we saved it as. And then here are the input arguments that it will take. So basically what's going to happen is we're going to pass in values for t, a, b, and c, and then it tells you here what a, b, c, t, x, and y need to be. So t, x, and y are vectors, a, b, and c are scalars. And then it's going to plug those values into this, evaluate x and y, and then output x and y for us to the command window. Something that's really neat when you're creating function files, when you use comments directly underneath that first line of the function where you created the function, if you do help compute xy, for example, then it's going to display a help window for you that will have it will display help to the command window that shows these comments that you created within the function file. So we'll just continue the example. If we were to type in the MATLAB command window using this syntax, so notice now it's U and V. It doesn't matter. The output variables are irrelevant. It's the order of them. Compute XY, and then here's our input argument for, what was it? T, A, B, and C. Again, pay attention to that order. So then it's going to go through, evaluate X and Y, and then it's going to produce the results for U and the results for V. So this is just variations of the function statement. That's kind of a lot of code there, and it can be a little bit difficult to decipher what is going on between each of these three examples. So watch the next video and I will go over this information for you. In some instances, the number of different variables that are transferred to the function can become large. In these cases, it may be beneficial for the function to share global memory of the script or function, or to create access to global variables for use by various other functions. So this, again, can be done through that global keyword. So let's look at an example. Let's say we want to transfer the values of a, b, and c in the function computeXY as global variables. This script would be what we would use here. So everything looks pretty much the same, but you can see now we have the global a, b, and c. And note that the blank spaces are required between each of these. The script then to call the function would be global a, b, c. And then we define what those values are equal to, And then again, we have our function here. When the function keyword is used more than once in a function file, again, that's referred to as a subfunction. So all other additional functions below that main function is a subfunction. The expressions comprising the first use of the function keyword is called the main function. We went over that. The subfunctions are only accessible to the main function and to other subfunctions within the main function file. So here's an example: compute the mean and standard deviation of a vector of numerical values. We're going to compute the quantities in a relatively inefficient manner just to illustrate the properties of subfunctions. So we have our two expressions here. We have m, which is going to compute the mean, and then we have s, which is going to compute the standard deviation. So here's an example of the syntax. So this here is our main function, this function for mean, standard, dev here, and then these here are sub-functions, okay? So we have function mean, that is going to compute our mean for us, and then standard dev is obviously going to compute our standard deviation. So what we have here is we're going to pass in the data, okay? So we have n, m, and s. So n is equal to the length of our data. How many elements or how many numbers do we have in that vector or matrix, whatever, of data? And then m is equal to the mean of data and n. S is equal to the standard deviation of data and n. So then what it's going to do is it's going to pass that into here, and then this will be evaluated. That'll be passed into this. And then the outputs will be shown as m and s for the mean and the standard deviation. So a script that might use this function and subfunction would be this, for example. So we pass in this vector 1, 2, 3, 4, and then the output is going to be our mean and our standard deviation. This vector v here is going to be passed in to our input arguments, which will then be evaluated in our subfunctions. So comparison of the usage of subfunctions, anonymous functions, and inline functions. Again, this is kind of a lot of syntax here, a lot of code. It can be a little bit difficult to read and even explaining so. So when I do the next video, I will show you this in MATLAB so that you can kind of see the difference a little better between them. So user-defined functions, function handles, and feval. Many MATLAB functions require that the user create function in a form specified by MATLAB. These functions use the feval function handle P1, P2, Pn. So function handle is the function handle. You're going to use the @ symbol to create the function handle, and then P1, P2, and so on are parameters that are passed into the function represented by function handle. So a function handle is a means of referencing a function and is used so that it can be passed as an argument in functions, which when evaluated is using feval. A function handle is again constructed by placing the @ symbol in front of that function name. So we have some MATLAB functions that operate on arrays of data. This just lists them here for you and then gives a short description of what those do. I will be demonstrating some of those in the next video for you. So fitting data with polynomials, let's consider the general form of the polynomial here. The coefficients ck are predetermined from this polyfit function here. So our input arguments are x, y, and n, where n is the order of the polynomial. C, so C1, C2, is equal to a vector of length n plus 1 representing the coefficients of the polynomial. And then x and y are each vectors of length m that is greater than or equal to the n plus 1. They are the data in which the polynomial is fitted. So again, I'll be demonstrating examples in the other video for you, but we'll just go over the general syntax here so you have an idea. To evaluate the polynomial, once we have determined C, we can then use polyval, where our input arguments are c and x new. So c is a vector of length n+1 that has been determined from polyfit, and then x new is either a scalar or a vector of points at which the polynomial can be evaluated. So in general, the values of x new in polyval can be arbitrarily selected or may not be the same as those values given in x. So this is just a continuation of our example here. These expressions can be combined, so if you wanted to put it into one line of code. So remember, the polyval, it was c and then x new. So c is just equal to the coefficients as determined by polyfit. So that's why we can just combine this into one line here. But note that this is if the coefficients c of k are not of interest to us. So here's just a continued example. This shows the actual syntax for an example that we could do to generate 10 points equally spaced along a sine curve from the interval 0 to 4 pi. I'll do this in the next video for you. We could also fit data with spline. So to generate a smooth curve that passes through a set of discrete data values, we use splines. The function that performs this curve generation is spline x, y, and x. So these are just, again, the general form here that you would use. So y is y of x. X and y are vectors of the same length that are used to create the function relationship y of x. And x, this one here, is a scalar or vector for which the value of y equals y of x are desired. In general, x, lowercase x, is not equal to uppercase x. So this is not equal to this. So again, here's another example that we're going to go through in the next video. We can also do interpolation of data. To approximate the location of a value that lies between a pair of data points, we must interpolate. So the function that does the interpolation is this here. U, v, and u are our input arguments. So in this case, v is v of u. U and v are vectors of the same length, and then the uppercase u, this last input argument here, is a scalar or vector of values for which u, for which v is desired. In general, again, the lowercase u, this one here, the first input argument is not equal to this last input argument. Here's another example that I'm going to demonstrate for you guys in the next video. We can also do numerical integration using the trapz function. So one can obtain an approximation to a single integral using this trapz here, where x and the corresponding values of y are arrays of numbers. So the function performs the summation of the product of the average of adjacent y values and the corresponding x intervals separating them. So here's another example that I will demonstrate for you. We can also do the area of a polygon using the polyarea function. So one can obtain the area of n-sided polygons where each side of the polygon is represented by its endpoints. So again, here's our polyarea. X and y are our input arguments. So x and y are vectors of the same length that contain the x and y coordinates of the endpoints of each side of the polygon. Each x and y coordinate pair is the endpoint of two adjacent sides of the polygon. Hence, for an n-sided polygon, we need the n+1 pairs of endpoints. So here's another example. We'll go over that shortly. We can also use user-defined functions. So these actually require user-defined functions. So F0 is one you might use. Here's the ODE 45. I'm going to do an entire video just dedicated to solving ordinary differential equations in MATLAB. This is hands down the function, actually the part of the entire course that usually causes the most problem for students, unfortunately. But I'm going to do my best to explain it to you guys, and I'm going to do lots and lots of examples. It's actually not that bad. It's just a matter of understanding what the syntax is and how to set up the function using ODE 45. So don't be concerned, don't be worried. We'll definitely get into that, but be sure you really pay attention when you watch that video. But here's some other ones here. fsolve is another one that you might use. It numerically solves a system of nonlinear equations for us. So here's a few of them. So we have f0. There are many equations for which an explicit algebraic solution to f of x equals 0 cannot be found. So in those cases, we can use f of 0 to find numerically one solution to the real function f of x equals 0 within a tolerance of t naught in either the neighborhood of x naught or within the range of some vector values. So the function can also transfer pj, where j is equal to 1 of 2, parameters to the function defining f of x. So the general expression for f0, we have z is equal to f0. Here's our function handles. So again, this is going to be the user-defined function that we create. X naught, we have some options in terms of our parameters, and then parameter 1, parameter 2. So z is the value of x, for which f of x is approximately 0. Function name is, again, the name of the function file with the extension .m that we create. X naught is equal to x naught, or x naught is equal to that array of values. And then p1, p2 are, again, those parameters. Options are set using the optim set syntax here. So the interface for the function required by f0 has a specific form. So you have to go function z equals function name x parameter 1 parameter 2. Then you have your expressions, and then z is equal to what your equation is. So what your f of x is. So where x is the independent variable that f0 is changing in order to find a value such that f of x is approximately 0. The independent variable must always appear in the first location. That's really important that you make note of that when using the f0. So here's an example that I will go through in the next video. We can also do, again, the numerical solutions of ordinary differential equations. There's some preliminaries that we need to discuss. So we must be able to put a system of differential equations as a function of the dependent variable, so k, into a set of first-order differential equations of this form, and to convert the initial conditions or the boundary conditions to a function of yj. So again, watch my video that's going to be dedicated specifically to solving ordinary differential equations. It's really, really useful. It's actually a pretty cool function. So we want to make sure that you guys know how to do that. It'll be helpful in some of your other classes. So the function ODE 45 returns the numerical solution to a system of n first-order differential equations over the interval t is greater than or equal to t naught and less than or equal to t final, subject to the initial conditions as stated here. The argument and outputs of ODE 45, so this is the general syntax that you have here. So t and y are going to be your outputs. Here's our ODE 45 function, and then we're going to create a user-defined function. It's going to be at our function name, our function handle, and then this here is our initial time, our final time, and then we have some additional parameters here. I'm not going to go too much into detail with this because, again, it's a lot of just notation and people tend to get really confused. So just kind of take a look, get an idea of the general format of the ODE 45 function, how we might set that up, and then watch my video where I go over this. The first argument of ODE 45, again, is the function name, which is a handle to the function or subfunction. So the subfunction takes this general form. So we have function y prime, this is just the name of our function, equals function name, so this is our handle, and then here is our input arguments to our expressions that will follow this. So t is the independent variable, y is a column vector whose elements correspond to yj, p1, p2 are the parameters passed into the function name, and y prime is a column vector of length n whose elements are as follows here. So again, here's our general form of the ODE 45 function here. Here's an example. This is one of the examples that I'm going to go over with you. I also have some additional examples of my own that I'm going to show you that I really feel will help to demonstrate how to use this function and kind of clear up some of the confusion that comes along with using ODE 45. So I'm just going to kind of skip through that here. We can also solve higher order differential, ordinary differential equations in MATLAB. Again, I'm going to show this because you have to kind of rearrange your function and do a little bit of manipulating to your differential equation in order to get it into a format that we can use in MATLAB. So again, I'm going to show that to you in the next video. Here's just more of the example. So this here just shows you kind of the general way that we would set up the ODE 45. So we have function ODE run 2. This is just the name of our function here. Here's our output variables. Here's our ODE 45. And then we're calling this function here. And then here is our argument. So we have our independent variable t, time, is from 1 to 10, and then y is 1. Okay, so boundary conditions. So we have a equals 1, and then dy equals a times y of 1. Again, don't worry too much about this syntax, just get a general feel for what's going on here. Second order differential equations, it's very similar, but now you can see because it's a higher order differential equation, for example, if it was a second order, we now have two of the conditions here, same time interval, but now we have dy1 and dy2, and I'll explain why we have to do this shortly. And that about sums it up. If you have any other questions, let me know. Otherwise, I'll just see you guys in the next video. Thanks so much. Bye.